All right then, as discussed on the previous video that here we're gonna do the partial fractions and the partial integrations as a revision of what we have learned in engineering mathematics 1. Now, when you talk about the partial fractions, what are we actually talking about? You know what is a fraction, right? But you need to understand that what are partial fractions and how do we see them? Now, given a rational expression in this form, our fraction can be given or presented in this form, where we have p of x divided by q of x, okay? And these are two functions because they are the functions that are defined by p of x value, q of x value. So that means these are defined as the functions. So now you have to understand that p of x in this equation over there and q of x are polynomials. And then the degree of p of x, it must be smaller than the degree of q of x. What do they mean when they say that? Now, for an example, let's say I have a fraction whereby my fraction will be x over x to the power of 2. The fraction at the top, it is a linear function. And then the function at the bottom, it is a quadratic function. We can see that the degree of these two functions, it is not the same. So the function that we find at the numerator, it has the smallest degree because its exponent is 1. And then the function in the denominator, it has the highest degree because its exponent is 2. So that means if you have a linear function at the top, that means you're supposed to have any other function, but you can start from quadratic moving forward, quadratic, cubic, and so forth. If you have a constant, for an example, let me just write any number. I'll just write 3. And then at the top, that means you're supposed to have x. I don't care what x plus 1 or 2x, as long as this is a linear function. Because we can see that at the top, we have a number which is a constant in this case, and then no degree. But at the bottom, which is our denominator, we have the highest degree compared to what we find at the top. So that means the function found in the numerator always supposed to have the smallest degree compared to the function that is found in the numerator. So if you have x to the power of 2, that means at the top is supposed to have x to the power of 3. If you have x to the power of 3, that means at the top is supposed to have x to the power of 4. So that means this statement over here, where they say this function of p of x, its degree supposed to be smaller than the degree of q of x, which is the function that is found at the bottom, which is in the denominator. So each and every time when you are given your rational functions with your polynomials, we need to always be able or look out for an opportunity to factorize our denominator completely, okay? But you will see what I mean when I say that when you solve different questions. Then for each factor in the denominator, right? Remember, q of x in that case, it will be factorized, meaning it will be given in the form of factors. And then after factorizing q of x, what are we going to do? Then for each factor in the denominator, we can use the following. For an example, let's have a look at case number 1. This is our fraction, right? And remember, the degree of the numerator is supposed to be less than the degree of the denominator. In this case, it's easy because we can see from the get-go that our function it is expressed in terms of its factors. So this is already factorized. So when you have a fraction that is factorized like this, where you can see the factors, the first factor is going to be x plus or minus a, x plus or minus b, x plus or minus c. These are the factors. So now we can decompose. Remember, decomposing is when you break something down. Composing is when, meaning from here, moving in this direction, we are decomposing, we are breaking it down. But from here, moving in that direction, we are composing. So that means you're going to have to add these two functions, add these three fractions together. After adding these three fractions together, we're going to get something that looks like this. But if you want to break this huge fraction over here, we're going to have to decompose it, which is that. Okay, so now here's the thing. After factorizing your denominator, you're going to take your factor, your first factor, which is x plus or minus a. You're going to write it over there. And then you're going to write it over any constant number or any constant. In this case, our constant, we'll call it a because it is unknown. We don't know it as yet. We're going to have to solve it so that we can know that this equation is equals to what over there. So, and if you have a look at this fraction, remember, the function that we find at the numerator is supposed to have the smallest degree compared to the function that we find at the denominator. In this case, it doesn't even have a degree, it's just a constant. And then here we have a linear function because you can see that it's x, not x plus x to the power of 2, x to the power of, it's just x to the power of 1. So that means this is proper way to do it. So that means here we're going to have our constant, and then here we're going to have our factor. Same applies. We're going to do the very same thing with the second factor, which is x plus or minus b. We're going to write our factor over there, and a constant. We can see that this factor, it has degree 1. Therefore, that means we're going to have a constant at the top, just like how I showed you over here. If your exponent is x to the power of 1, that means you're going to have a constant. But if you have something like x to the power of 2 plus x plus 1, something like that. So that means at the top, you're going to have a linear function because at the bottom, it is a quadratic. So then it's going to be something like this, maybe x plus b. You understand what I'm saying? You're going to have a linear function because you have a quadratic. That's what I mentioned over here. If you have a quadratic, you're going to have a linear function. But make sure that your gradient and the y-intercept are going to be the constants, are going to be the numbers that we actually do not know. At some point, you're going to have to solve for those numbers and continue with our problems. Now, that's what you're going to do throughout the entire equation of case number 1, okay? So now, this is what I'm going to do. You can go through case number 2, you can go through case number 3, it is still fine. But what I'm going to do right now is I'm going to do some problem solving under case number 1 first, and then we'll jump to case number 2 and case number 3 and so forth. So now let us use case number 1 to solve these kind of questions. So now what we see over here, we are given, we have example number 1. We are given a rational fraction, in this case, x. Here's our fraction, x plus 7 divided by x to the power of 2 subtract x subtract 6. This is a fraction, right? And have a look at the denominator. Have a look at the numerator. Numerator is a linear function. Denominator is a quadratic function. So this is a proper way to represent this fraction. So that means we need to decompose the following fraction. But the question is, how are we going to decompose it? Before we can apply the integration, we're going to learn how to how to decompose this fraction first. So that means decomposing this fraction, I'm going to rewrite it as it is. So that means we have x plus 7 divided by x to the power of 2 subtract x subtract 6. So now this is what I'm going to do. Remember, the first step is you look out for an opportunity to factorize. If it is factorized, then it is fine. But if it cannot be factored, that means we're going to have to jump to case number 2. But now let's have a look at this fraction. Are we able to factorize the denominator? Yes, we are able to factorize the denominator. So that means, how are we going to do that? Let me write this as it is. So that means at the top, we're going to have x plus 7 divided by, now let us try to factorize our denominator. Factors of x squared is going to be x, and x of 6 is going to be 2 and 3. And therefore the bigger number, negative, and that one will go there. We know how to factorize this. So now we managed to factorize this expression over here at the denominator. So that means we're going to have something that looks like this. Now we have our factors at the denominator. Now, this is what you're going to do. We're going to decompose this fraction, right? So let us decompose this fraction over here. So our fraction is written to be, I'm going to rewrite it. So we have x plus 7 divided by, we have x plus 2, we have x subtract 3. And therefore, this is what we are going to do. Remember, to decompose these fractions, our first factor is going to be x plus 2, right? But now what will be our numerator? It's supposed to have the lower degree, right? Because here we have just the x, which is linear function, meaning at the top you're supposed to have a constant. In this case, we're gonna start with constant A. We can just call it constant A. Call it Z, can call it Y, doesn't matter. But alphabetically, we choose to start with A because that's the first factor that we're gonna deal with. Now, the second fraction, as we decompose this fraction, is we're gonna start with we're gonna jump to our second factor, which is x subtract 3. We're gonna write our second factor, which is x plus 3. It's a linear function again. That means on our numerator is supposed to have the lowest degree or the smallest degree. In this case, we just have to write the constant because we have a linear function at the bottom. So for a fact that we wrote A, we can repeat that. So that means we can have constant B in this case. And therefore our fraction has been decomposed. But this is not the final answer because our decomposition, it is in the form of a constant, and these constants are unknown. We need to solve for those constants. We need to solve for A and B and rewrite this expression once more again with known values of A and B. But the question is, how are we going to determine the value of A and B? Now, this is how we're going to determine the value of A and B. We're going to work with this equation now, right? So that means on this side of the equation, I'm going to have to combine these two fractions, but I'm just going to write this as it is. So I'm going to have x plus 7 divide by, here I have x plus 2 multiply by x subtract 3, which will be equals to, let me combine these two fractions over there. I'm going to write my long division line, and I'm going to multiply my denominator because I want to combine these two guys over here. So that means here I'm going to have x plus 2, and therefore there I'm going to have x subtract 3. And therefore, now to combine these two guys over here, x plus 2 goes in times into this. X plus 2 will cancel that, and then I'm going to left with x minus 3. So that means I'm going to have a x minus 3. And therefore, let's move to this fraction. Then x minus 3 will cancel x minus 3. We're going to left with x plus 2 multiplied by b. It's going to be b multiplied by x plus 2. And therefore, now this will be a combined fraction of these two separated fractions. And therefore, we just cross multiply or we multiply by the same factor. So meaning if you multiply this side and that side by this factor over here, this will cancel that. And therefore, our fractions will fall. We're going to have x plus 7, which will be equals to a x subtract 3 plus b. And therefore, here we're going to have x plus 2. Now we have the equation that looks like this. Remember, we need to solve for a and b. That's our aim, so that we can rewrite those numbers over there. And therefore, this fraction is now decomposed. So to do that, this is what we are going to do. Ne? We are going to let our x value to be any other number, but it's important, or we need to strategize, or we need to know how to substitute the value of x, which value of x we need to pick. We do not just pick because we have to. Now we can see that a, it is multiplied to this bracket over here. So we want to get rid of a so that we can left with b in this equation, and then we solve for b. So how are we going to do that? We're going to have to let x first. We're going to have to let x to be equals to positive 3 because we can see that inside of this bracket we have negative 3. So that when we add 3 there, this gives us 0, and 0 multiplied by a, we no longer have a anymore. We have b, and then we solve for b, okay? So that's what we're going to do. We're going to let x to be equals to that. And therefore, we're going to substitute the value of x. We say our x is 3. That means we're going to have 3 plus 7 on this side of the equation, which will be equals to, we have a there, and then we substitute 3, subtract 3 over there, plus substitute, we have b here, and then there we're going to have 3 plus 2 over there. And therefore now what will be 3 plus 7? It's going to give us 10 on this side of the equation, and then we're going to have 0, and therefore this side we're going to have 5b. We divide both sides by 5, therefore the numerical value of b will be equals to, I think 2, yeah, will be 2. 10 divided by 5 will be 2. Now we are done with the value of b. We need to solve for value of a. Once more again, we're still gonna use the same technique or the same strategy where we're gonna have to let x. So in this case, we're gonna have to let x to be equals to how much? We go back to our original equation. This is our original equation. Now we got rid at a, we managed to solve for b. Now we need to solve for a, So that means we're gonna have to substitute negative 2 over there. So that means we're going to let x to be equals to negative 2, and therefore we go back to the original function. We're going to substitute negative 2 where we see x. So the original function here, we have negative 2 plus 7 which will most probably be equals to a, multiplied by -2, -3, and therefore plus b, multiplied by -2 plus +2. And therefore, -2 plus 2 in this case is going to be how much? Most definitely it's going to be +5. I think it's going to be +5 is equals to this and that. We're going to have -5a, and therefore that will be 0. Now we divide both sides by -5 so that we can solve a. We're going to get -1. Therefore, we can see that this fraction over here, which is this original fraction, x plus 7 divide by x to the power of 2 subtract x subtract 6 will be equals to which decomposed fraction? Now we know that we know the value of a, which is -1. So that means we have -1 all over x plus 2 plus what is the numerical value of b? We just found that b is equals to 2. We substitute 2 over there. We're gonna have 2 over x subtract 3. And therefore, this is how we solve this question over here. Now we're gonna have to jump to the next example. So here we were just decomposing the fraction. Now here we have example number 2, where we need to evaluate this, where we need to evaluate this integration over here. So now, because we did these things in EMA 1, we're not gonna dwell too much on the basics. We're just solving these things just to remind ourselves on how to solve these, okay? So they want us to evaluate the integral of this fraction, which is a fraction with polynomials. Rational fraction, we have x plus 7 divided by x to the power of 2 minus x subtract 6. We need to integrate this. But the question is, how are we going to integrate this? There are many methods on how to, obviously, we've learned, but the thing is, some methods, they don't work. Use substitution, integration by parts, many techniques that we can use to integrate. But you can see that here, the only way for us to integrate this is when we use the partial integration. So we're going to use what you call the partial integration. Spell correctly, right? So we're going to use partial integration to evaluate this integration over here, okay? So now I'm going to rewrite this as it is. So we have integral of x plus 7 divide by x to the power of 2 subtract x subtract 6 dx. This will be equals to, remember, we have already, if you have a look at the previous example, which is example number 1, this is the fraction, right? It is the same fraction that we did. So we don't have to start from the get-go and get here. We can just take this thing as it is because we saw that this is how we actually decomposed this fraction. Okay, it is already decomposed. We can just take it from here. So that means we can simply tell that the integral of this fraction is the same as the integral of this composed fraction. So we're gonna have -1 over, let me go back a little bit, x plus 2, right? Plus 2 over x subtract 3, x subtract 3, close bracket, dx, right? These two things are exact same thing. But now here we are actually integrating this using partial integration. So now using partial integration to integrate this, let us integrate each fraction because they're separated. We know laws of integration. We have learned that when you have plus sign, you can just separate them, and you know how to do that. You know the drill. So let us start with this fraction. We're going to take out negative as a factor. So out of the integral sign, so we have negative integral of 1 over x plus 2 dx, right? Plus, now we're going to focus on this fraction. We're going to take 2 as a constant out of the integral sign. Here we have 2, and then therefore we're going to left with what? Then we're going to left with 1 over x subtract 3 as well as dx. Now, integrating expression like this, you have learned or you have formula sheet on how to integrate these things. Understand can be a little bit challenging, but make sure if you are practicing, you have your formula sheet by you, or I don't know, maybe the techniques that you might have so far. So now the integral of 1 over x plus 2, we're going to use natural logs, which is ln, right? We have negative ln bar absolute, so yeah, x plus 2 bar plus, and then what is the integral of 1 over x subtract 3? We write our 2 there. We have ln x, sorry, bar, x subtract 3 bar. And then remember, these are definite or infinite integration. They don't have the bounds or they don't have the boundaries, so we just have to introduce the constant after integrating this, and therefore this will be our final answer.